Here was a day, 4.5 billion years ago, when this planet did not exist. And there will be a day, billions of years from now, when it does not exist again. Everything in between, every ocean, every mountain, every living thing that has ever drawn a breath happens in the part we are about to walk through, in the exact order it actually happened. You will watch a ball of molten rock get struck by a second planet and give birth to the moon. You will watch the air itself turn poisonous twice in 2 different directions. You will watch a forest floor breathe air so rich that insects grew wings the size of a hawk's just to carry them. You will watch 96% of everything alive on Earth die in a single geological instant, and then watch life claw its way back anyway. You will watch a mountain fall out of the sky and end the age of dinosaurs in an afternoon. And near the very end, in the last few seconds of a 4.5 billion year story, you will watch something stand upright, look up at the stars, and start asking why. But to understand how any of that happens, we have to go back, all the way back, to the moment there was no Earth at all, only dust and gravity and time. 4.6 billion years ago, this entire solar system was nothing more than a spinning disk of dust and gas circling a newborn sun. Gravity did the rest. Grain by grain, rock by rock, the debris clumped together, and within roughly 10 million years, a blink of an eye by planetary standards, Earth existed as a distinct object in space. It looked nothing like it does now. There was no blue ocean, no green continent, no sky you could breathe. There was only an ocean of molten rock, glowing at temperatures hot enough to vaporize steel, under a black sky lit by a much dimmer, younger sun. And then, roughly 4.5 billion years ago, something the size of Mars slammed into it. Scientists call the impactor Theia. The collision was violent enough to melt both bodies into a single spinning cloud of vaporized rock. And out of the debris that spun into orbit, gravity built something new. The moon cooling into a companion so close that early nights on Earth were lit almost as bright as day. This isn't guesswork dressed up as fact. Researchers at institutions including the University of Chicago have spent decades matching lunar rock samples brought back by Apollo astronauts to the chemical fingerprint Earth's mantle would carry if this exact collision happened. And the match, again and again, comes back nearly perfect. For the next several 100 million years, Earth remained what geologists call the Hadean, named fittingly after the underworld. Volcanic, airless in any breathable sense, bombarded constantly by leftover rubble from the solar system's formation. If you stood on its surface, you would see rivers of lava wider than the Mississippi, a sky choked with ash, and a moon looming close enough to swallow a third of the horizon. Nothing was alive. Nothing could be. And yet, tucked inside zircon crystals, barely wider than a grain of sand, found decades later in the Jack Hills of Western Australia, is evidence that liquid water existed on this hellish surface far earlier than anyone expected. As far back as 4.4 billion years ago, water on a planet that looked like hell. That single detail is the first thread connecting the dead rock we started with to everything that was about to happen next. Somewhere in that early water, in a crack in the ocean floor, or a shallow tidal pool, or possibly both at once, something crossed a line that has never been crossed the same way since. chemistry became biology. Nobody alive today watched it happen, and no fossil captures the exact instant. But the leading hypothesis, backed by researchers at institutions like the Max Planck Institute and NASA's astrobiology program, points to hydrothermal vents, cracks in the sea floor where mineral-rich water, heated by the planet's own molten interior, pours out into cold ocean water. The chemical gradient at that boundary is exactly the kind of energy source simple chemistry needs to start building the first self-copying molecules. By roughly 3.8 to 3.7 billion years ago, the evidence gets harder to argue with. In Isua, Greenland, geologists have found rock formations containing chemical signatures that on Earth today are produced almost exclusively by living organisms. If that reading holds, life was already established less than 1 billion years after the planet itself finished forming. And it was small, impossibly small. A single cell, no nucleus, no visible structure at all under anything but a modern microscope. The kind of organism you could fit 200,000 of inside a single grain of sand. This is Luca, the last universal common ancestor, the single lineage that every living thing on Earth today, every whale, every mushroom, every human being reading this sentence in their head, ultimately descends from. For the next 2 billion years, roughly, life didn't get much more complicated than that. Single cells floating in warm, iron-rich oceans, doing very little except surviving and copying themselves. It is, by a wide margin, the longest chapter in this entire story, and one of the least dramatic. But one small group of these cells was about to do something that would rewrite the entire chemistry of the planet. They were about to learn how to eat sunlight. And the waste product of that discovery was about to become the most catastrophic pollutant Earth had ever produced. Cyanobacteria, simple photosynthetic microbes, worked out how to split water molecules using sunlight, capturing the hydrogen for energy and releasing oxygen as pure waste. For the first billion years or so, that oxygen barely mattered. It was quickly absorbed by iron dissolved in the oceans, rusting the seas from the inside out, and settling on the ocean floor as the vast banded iron formations still mined today for steel production. But eventually, roughly 2.4 billion years ago, the oceans ran out of iron to absorb it. Oxygen started building up in the atmosphere itself for the first time in Earth's history. And to almost everything alive at that point, it was lethal. To organisms evolved entirely without it, oxygen worked like a slow poison, tearing apart the delicate chemistry, keeping their cells alive. Geologists call it the Great Oxidation event, and by some estimates, it may have wiped out the vast majority of life that existed on Earth at the time. A mass extinction almost 2 billion years before the word dinosaur would ever mean anything. The irony is heavy. The same gas every animal on Earth today depends on to breathe began its history as one of the deadliest pollutants this planet had ever produced. What followed was stranger still. For the next billion-plus years, a period geologists have nicknamed, almost apologetically, the boring billion, evolution appears to have nearly stalled. Life persisted, it diversified slowly, but nothing built a body, nothing grew an eye. Whatever conditions life needed to make its next leap simply weren't there yet. Then, somewhere around 650 million years ago, the entire planet nearly froze solid. Twice. Geologists call it Snowball Earth. and the evidence is written directly into the rock. Glacial deposits dating to this exact window, found not at the poles but near the equator, meaning ice sheets may have reached from pole to pole, turning the entire planet into a single frozen ball, reflecting most of the sun's heat straight back into space. It should have been the end of the story. Instead, it became the trigger for the next one. Volcanoes, unaffected by surface ice, kept pumping carbon dioxide into the atmosphere for millions of years, with nowhere for it to escape to. Eventually, the greenhouse effect built up so far past a tipping point that the planet flipped violently in the other direction, thawing in what researchers believe was a geological eye blink, triggering catastrophic rainfall and flooding the oceans with nutrients scraped straight off newly exposed continents. And in the aftermath of that violence, evolution did something it had not managed in 3 billion years of trying. It stopped being simple. Around 541 million years ago, in a burst so sudden that Charles Darwin himself worried it might disprove his own theory, complex animal life exploded into existence in what's now called the Cambrian Explosion. In a window that may have lasted as little as 13 to 25 million years. An eye blink on the scale of this story. Nearly every major animal body plan alive today made its first appearance. Shells, legs, eyes, spines. The best window into this event sits in a single quarry in British Columbia, Canada. The Burgess Shale, a fossil deposit so exquisitely preserved, it captures soft tissue that almost never survives. Studied in detail by institutions including the Royal Ontario Museum for over a century. One of the animals it preserved still unsettles paleontologists today. Anomalocaris, a meter-long swimming predator with 2 grasping claws at the front of its head and a circular, plated mouth. According to a 2011 study published in Nature, its compound eyes contained an estimated 16,000 individual lenses each, more than almost any living arthropod, making it, quite possibly, the sharpest-eyed hunter the ocean had produced up to that point. For scale, it was longer than a scuba diver is tall, patrolling reefs built not from coral but from stacked colonies of sponges and algae. Why did this happen so suddenly after 3 billion years of almost nothing? Nobody has a single confirmed answer. Rising oxygen levels, an evolutionary arms race triggered by the first true predators. Even the evolution of vision itself, letting animals finally see and hunt and hide. All of it is on the table and none of it is fully settled. What is certain is this: the moment eyes and jaws entered the ocean, evolution stopped being a slow drift and became something closer to a war. And the next 400 million years would be fought first in the water and then, for the first time in Earth's history, on dry land. Life had existed exclusively in water for well over 3 billion years. Land, by comparison, was closer to a dead moonscape. Bare rock, no soil, no shade, scoured by ultraviolet radiation with no ozone layer thick enough yet to block it. The first colonists weren't animals, they were plants, or more precisely, their algae ancestors, creeping onto damp shorelines roughly 470 million years ago, according to fossilized spores studied by researchers, including teams at the University of Cambridge. Simple, low, moss-like at first. But plants change the ground they grow on. Roots break rock into soil, and soil holds water. Land was slowly becoming somewhere worth visiting. Animals followed the food, arthropods, ancestors of today's insects, and spiders were among the first, small and armored enough to survive without the water support. But the real turning point belonged to fish. By the Devonian period, roughly 375 million years ago, one lineage of lobe-finned fish had evolved something unusual: thick, muscular fins with internal bones arranged almost like a primitive arm. The most famous transitional fossil, Tiktaalik rosea, discovered in 2004 on Ellesmere Island in the Canadian Arctic by a team including researchers from the University of Chicago, shows the anatomy caught mid-transformation. A fish unmistakably, but one with a flexible neck, a flattened skull, and fins capable of propping its body up in shallow water or soft mud. It was not designed to walk. It was built to survive in the shrinking, oxygen-poor shallows, where staying in open water might mean getting eaten, and pushing toward the edge might mean finding food nothing else could reach. Evolution rarely leaps toward a destination. It stumbles forward, one marginal advantage at a time. Within a few million years, genuinely fast by evolutionary standards, descendants of these fish had true limbs, air-breathing lungs, and were spreading across a continent that had never once felt a spine move across it before. The invasion of land was underway, and it was not going to slow down. By the Carboniferous period, beginning around 359 million years ago, land had transformed completely. Vast, swampy forests stretched across the continents, towering stands of club mosses and tree ferns, some over 30 meters tall, roughly the height of a 10-story building. These forests did something no ecosystem before them had managed. They buried carbon faster than it could decompose, layer after layer for tens of millions of years. Carbon that would eventually compress into the coal seams still mined across the world today, which is exactly why geologists named this period after it. And burying that much carbon had a side effect. Oxygen levels in the atmosphere climbed to an estimated 30 to 35%, far above the 21% we breathe today. For insects whose bodies absorb oxygen passively through tiny tubes rather than lungs, more available oxygen meant their size limit expanded dramatically. The result was Meganeura, a dragonfly-like insect with a wingspan that could stretch past 65 centimeters, wider than a hawk's, patrolling the humid understory on wings that would look, at this scale, more like a small aircraft than anything you'd swat off a picnic table. Alongside it crawled Arthropleura, a millipede relative over 2 meters long, the largest land-dwelling arthropod ever confirmed to exist. It was, by every measure, one of the strangest ecosystems this planet has ever hosted, and it could not last. Oxygen levels this high made forest fires burn at a ferocity barely imaginable today, and eventually, the climate itself was about to turn against nearly everything alive. The Permian period ended roughly 252 million years ago, in what remains, to this day, the single worst catastrophe complex life has ever survived. Paleontologists simply call it the Great Dying, and the numbers involved are almost too large to process. Current estimates published by researchers, including teams at the University of Bristol, put the death toll at up to 96% of all marine species and roughly 70% of land vertebrate species. Not endangered, extinct, gone. The trigger appears to have been geological, not cosmic. In what's now Siberia, volcanic activity on a scale almost impossible to visualize. A region called the Siberian Traps poured out enough lava to bury an area larger than the continental United States, under rock more than a kilometer thick in places, over the course of roughly 1,000,000 years. That alone would have been catastrophic. But the lava didn't just bury the surface. It burned straight through vast underground coal and oil deposits on its way up, releasing decades' worth of greenhouse gas in a geological instant. Global temperatures spiked, oceans acidified, oxygen levels in seawater collapsed into vast, lifeless dead zones that some researchers estimate stretched across the majority of the ocean floor. Picture the dragonflies the size of hawks and the sail-backed predators the size of cars from the world we just described, and picture nearly all of it disappearing within a span that, geologically speaking, barely registers as a moment. It was not simply an extinction, it was closer to a full reset of the experiment of complex life run for the second time in this story alone. And yet, and this is the part that still genuinely surprises paleontologists, life did not stay down. Within a few million years, in the empty, damaged ecosystems left behind, a new group of reptiles was already quietly diversifying in the shadows. Small, unremarkable, built for survival rather than dominance. Nobody watching the smoking ruins of the Permian world could have guessed what these particular survivors were about to become. The Triassic period that followed was, for millions of years, a slow, difficult recovery. Ecosystems rebuilt themselves gradually, dominated at first by tough, adaptable survivors rather than anything spectacular. But somewhere in this recovery, a specific lineage of small bipedal reptiles began experimenting with an upright stance. Legs positioned directly underneath the body rather than sprawled to the sides. The same posture that lets a modern greyhound sprint far more efficiently than a modern lizard. By around 230 million years ago, fossils like Eoraptor from what's now Argentina, barely the size of a large dog, show the unmistakable early anatomy of the group that would eventually be called dinosaurs. They were not yet the dominant animals on the planet. That title still belonged for now to large crocodile-like reptiles that outnumbered and outsized them at almost every turn. Then, roughly 201 million years ago, another mass extinction, smaller than the Great Dying but severe, wiped out a large share of those competing reptile lineages, widely linked to another burst of catastrophic volcanic activity as the supercontinent Pangaea itself began tearing apart. The dinosaurs, for reasons still debated, came through it in far better shape than their rivals. With the competition gone, they didn't just survive. They exploded outward into every ecological role left standing. Swift, hollow-boned hunters chasing prey across open plains, armored grazers built like living tanks, and eventually, the first true giants this planet had produced since the Cambrian seeds. The age of dinosaurs had begun, and it was about to last vastly longer than humans have existed, by a margin most people badly underestimate. For the next 165 million years or so, across the Jurassic and Cretaceous periods, dinosaurs ruled nearly every landmass on Earth. To put that span in perspective, the time separating Stegosaurus from Tyrannosaurus rex is longer than the time separating Tyrannosaurus rex from you. Sauropods, the long-necked giants like Argentinosaurus, grew to lengths estimated at 30 meters or more, roughly 3 school buses, parked end to end, and may have weighed as much as a fully loaded Boeing 737. Growing that large from an egg the size of a grapefruit required one of the fastest sustained growth rates ever documented in a land animal. Some estimates suggest these titans could gain the weight of an adult human every single day during their adolescent growth spurt. Predators kept pace. Giganotosaurus and its relatives hunting these titans across what's now Argentina carried blade-like serrated teeth built not to crush bone like a T-Rex, but to carve deep, bleeding slashes and simply wait. Fossil bone beds containing multiple individuals of the closely related Mapusaurus, uncovered near Argentina's Museo Carmen Funes, have led some researchers to suspect these predators may have hunted in coordinated groups, a claim still debated, but one that would make sense of how anything managed to bring down prey that outweighed it many times over. In the skies above, pterosaurs like Quetzalcoatlus reached wingspans estimated at up to 11 meters, roughly the wingspan of a small private jet, making them, by a wide margin, the largest flying animals this planet has ever produced. In the seas, marine reptiles like Mosasaurus, unrelated to dinosaurs entirely, grew into apex predators over 15 meters long, and healed bite wounds found on other Mosasaurus skeletons suggest they fought, sometimes each other, with a viciousness that left scars. This was not a quiet planet. It was, by nearly every measure available to paleontologists, the most extreme experiment in size and violence complex land life had ever run. And on an ordinary afternoon, 66 million years ago, it ended in about as much time as it takes to read this sentence. The object was roughly 10 kilometers across, wider than most cities, traveling at somewhere close to 20 kilometers per second when it struck what's now the Yucatan Peninsula in Mexico. The impact confirmed through decades of geological work, including core samples drilled directly into the Chicxulub crater itself, released energy estimated at billions of times the force of the atomic bomb dropped on Hiroshima. Within minutes, everything within 1,000 kilometers was almost certainly incinerated by the blast wave and the falling debris raining back down as superheated rock. Within hours, megatsunamis were tearing across ocean basins, and earthquakes far more powerful than any in recorded human history rippled around the entire planet. But the blast itself was not what ended the age of dinosaurs. The real killer came after: vaporized rock and sulfur thrown high into the atmosphere, blocked enough sunlight that researchers estimate global temperatures may have dropped for months, possibly years, plunging the planet into a prolonged photosynthesis-starving winter. Plants died first, then the animals that ate them, then the animals that ate those animals. Every land animal larger than roughly a house cat appears to have gone extinct, a size cutoff so consistent across the fossil record that paleontologists still cite it as one of the extinction's strangest, sharpest patterns. The last non-avian dinosaurs, animals that had ruled this planet for 165 million uninterrupted years, were gone. It was not simply the end of an era. It was proof that size, strength, and total dominance mean nothing against a threat evolution never had the chance to prepare for. And yet, in the wreckage, something survived that almost nobody would have bet on beforehand. Small, warm-blooded, burrow-dwelling creatures, barely bigger than a modern shrew. the early ancestors of every mammal alive today, including us. Their size, once a disadvantage in a world ruled by giants, had suddenly become the very thing that let them shelter underground, eat almost anything, and simply wait out a catastrophe built to kill giants first. With the dinosaurs gone, an entire planet's worth of ecological space, every niche, every role, every empty throne was suddenly, violently up for grabs. What followed is a period researchers sometimes nickname the Age of Mammals, though for the first several million years it looked nothing like triumph. Early mammals were small and cautious, still competing against surviving crocodilians and enormous flightless birds that, for a brief window, were genuinely apex predators on some continents. But mammals had one advantage no group before them had fully exploited: live birth and extended parental care, letting offspring learn and adapt far faster than anything hatching alone from an egg into a hostile world. Within roughly 10 million years, a geological sprint, mammals had diversified explosively, filling niche after empty niche. Early primates climbing into newly expanding forest canopies, early hoofed mammals spreading across open plains, and eventually ancestors of whales wading back into the very ocean their own distant ancestors had crawled out of hundreds of millions of years earlier. Some grew enormous. Indricotherium, a hornless rhinoceros relative that lived roughly 30 million years ago, stood taller than a modern giraffe at the shoulder, and may have weighed as much as 4 African elephants combined. Very possibly the largest land mammal ever confirmed to exist. Megatherium, a ground sloth the size of a modern elephant, and Smilodon, the saber-toothed cat, whose curved canines could exceed 28 centimeters, followed millions of years later in an Ice Age world about to test every one of these giants in ways the warm Cretaceous never had. Because the planet once again was cooling, and this time the cooling was about to shape the one lineage that would eventually turn around and start asking questions about all of it. Starting around 2.6 million years ago, Earth entered a long cycle of ice ages, with glaciers repeatedly advancing and retreating across the northern continents in rhythm with subtle wobbles in the planet's orbit. Sea levels dropped low enough during the coldest periods to expose land bridges connecting continents that are separated by open ocean today. Somewhere in East Africa, during this unstable, unpredictable climate, one particular lineage of ground-dwelling apes was under constant evolutionary pressure to adapt, and adaptability itself became the trait natural selection favored most. Bigger brains, more flexible diets, increasingly complex tools. The earliest fossils confirmed as Homo sapiens come from Jebel Irhoud, Morocco, dated in a landmark 2017 study published in Nature to roughly 300,000 years ago, pushing the origin of our species back further than almost anyone expected. For most of that 300,000-year history, humans were not the dominant force on this planet. Far from it. They were one mid-sized primate among many, sharing the landscape with cave bears, giant hyenas, mammoths, and at least 4 other human species, including Neanderthals in Europe, most of whom would eventually vanish for reasons still actively debated among researchers. What changed things wasn't strength. Humans are not the fastest, strongest, or best-armed animal to ever walk this planet. Not remotely. It was something else. Language complex enough to plan collectively, and culture capable of accumulating knowledge across generations instead of losing it every time an individual died. If you compressed all 4.5 billion years of this story into a single 24-hour day, complex animal life wouldn't appear until around 9:30 p.m. Dinosaurs would rule from roughly 10:56 p.m. until 11:39 p.m. And Homo sapiens, every human who has ever lived, every war, every empire, every word ever written, would occupy the final 6 seconds before midnight. 6 seconds out of an entire day. That is the honest scale of everything you have ever personally known, set against the actual age of the ground beneath your feet. And the story does not stop at midnight. Every process that built this planet, volcanic, chemical, orbital, is still running right now, exactly as it has for 4.5 billion years. The tectonic plates that once assembled and tore apart Pangaea are still moving, roughly at the speed your fingernails grow. Earth has already ended in a sense, at least twice. Frozen solid as a snowball, and later stripped of 96% of everything alive on it, and rebuilt something new each time, more complex than what came before. Nothing about that process required humans to be watching, and nothing about it guarantees we'll be here to watch the next chapter either. But for 6 seconds before midnight, something on this particular pale, rocky planet learned to ask where it came from and started digging through 4.5 billion years of rock and ice and fossilized bone to actually find out. That part of the story is still being written, and whatever comes next, the next ice age, the next mass extinction, the next 6 seconds nobody has lived yet, is already being decided by choices being made on this planet right now, whether anyone alive today chooses to notice or not.